Okay, here's our third A-level video on the gravitational potential energy. It'll probably finish off this topic. I'm going to try and draw your knowledge from GCSE and then draw in what we've already learnt from fields. So let me start with gravitational potential energy, as you learnt in year 9, is mg delta H. Mass times 9.81 on Earth, or 10, and the change in height, moving from one point to another. That's I think we represented it like this. Really, you had you had a mass and a change in height, and the energy was that times g, whatever g was on Earth. You multiply them together. Now, this has always yielded positive numbers, so that's always been positive. However, if we were to move an infinite distance away from an object, then the gravitational potential energy at that point would be 0. However, just as we knew that there was work done in order to move this object, a force times a distance, in order to move this distance up, the work done in trying to achieve this would be positive. So we have a positive number, the work done, getting us to 0, and if this is positive, then whatever we start with must be negative in order for that to equate itself. So essentially what I'm trying to say is that the gravitational potential energies are going to always be negative. Always going to be shown to be negative. So this is the convention which we use. And one to bear in mind, it also implies that things are attractive. So if you want to try and remember it, think attractive. Good. Okay then. So let's take this equation here and just remind ourselves again that we could talk about something called potential. And the potential is referencing 1 kilogram, or a unit mass. In other words, what's the gravitational potential energy for 1 kilogram? And in this case, it's just g delta H. And we like to talk about potentials much more than we do the actual GP, because we can reference one planet to another planet much more easily. So now let's talk about the potential, but not using something close to the Earth. Let's look at something which is much further away from the Earth, or what we've done before. G, a change in distance. And G we know to be minus gm over r squared by a change in r. So if I want to look at this quite simply, I can say that, well, this distance and this distance cancel out with each other. I know it's not the case strictly, but essentially what I'd have is the potential would be minus gm over r. Okay, so this is the equation we're going to be working from. But bearing in mind, of course, and this is what confuses everybody, if we do a simple equation like this one up here, and I look for a change in height. Let's imagine something changes a certain distance. Let's try and work out the potential from this equation. Okay, so first of all, let's go with that simple example. Let's say, in this instance, G is 10 newtons per kilogram. I've gone 10 meters and I've got 10 kilograms. So therefore, in the first instance, if this were a uniform field, my potential would be GH, which is G change in height, 10 by 10, giving me 100 joules per meter. Of course, energy by that. Or indeed, it would give me, let's leave it as joules per meter. Now, what's the potential if I was thinking about this in like a radial field, because this is dealing with a radial field. And of course, this is uniform. Let's see if they coincide to be the same. We use the same example again, 10 meters, but this time I know that the center of the Earth sits 6,400 kilometers away from me. 10 kilograms again, and big G, of course, is 6.67 times 10 to the minus 11. So what's my potential? Well, my potential is going to be minus Gm over R, but I'm looking for the change from the centre in both accounts. So I've got to look at the difference between this one and this one. So I can't simply do that. That does not work. What I need to do is I need to do Gm 1 over R1 minus 1 over R2. So what does that give me? That gives me minus 6.67 times 10 to the minus 11 by 6 times 10 to the 24 multiplied by, I'll put it down here, sorry, that's a bad way of putting it, 6.4 times 10 to the 6 minus 1 over 6.4 times 10 to the 6 plus 10, close brackets. And the change, once you plug it all in, the change in GP gives me 977 joules per metre. And I hope you can agree that that and that, oh, sorry, 99.7, they're in quite good agreement. So what we're doing from here on out is we're looking at the radial fields, and hopefully the GCSE knowledge is actually being matched by the potential radial fields. So let's take a look a little bit more clearly at some examples. So let's have a look at, here we get the surface of the Earth. And let's imagine I'm going to, no, let's go for Mars just to change things around. I've got 2,400 kilogram object, and I'm on Mars, so the mass of Mars is actually 10 times less than that of Earth, 6.4 times 10 to the 23 kilograms. The radius is 3394 kilograms. And let's say that I want this to launch and meet the lander to meet something at, I'll make life easy, 12,000 kilometers from the center. Yeah, that's right. So what's the change in potential in moving from one to the other? If you think you know the answer, hit pause. Otherwise, here comes the answer. Okay, first of all, I want the change of potential, which is minus Gm over R. And then I'll want the gravitational potential energy, GPE. So why don't I bolt it all together? Minus 6.67 times 10 to the minus 11 by 6.4 times 10 to the 23, it's Mars, remember, by, and I want 1 over surface, 3.394 times 10 to the 6, minus 1 over, that's going to be 3, that's going to be 12 times 10 to the 6. Plugging it all in gives me an answer of minus 2.2 times 10 to the 10 joules. Okay, what's the potential on the surface of the Earth? So at the surface of the Earth, oops, wrong one. What's the gravitational potential energy at the surface of the Earth of a 100 kilogram man, knowing the mass of the Earth is 6 times 10 to the 24, and the radius is equal to 6.4 times 10 to the 6 meters. Okay, if you think you know, hit pause, otherwise here comes the answer. GPE is going to be m delta V, and I'm looking for just the potential from referencing the center. So it's not a change anymore. I'm not looking for a change, I'm just looking for the potential, which means I got my 100 by Gm over R. 100 by 6.67 times 10 to the minus 11 by 6 times 10 to the 24. Divide that by 6.4 times 10 to the 6 gives me one I haven't done earlier. Plugging it into the calculator. 6 to the xp 24 divided by, it's something like 62.5 megajoules per kilogram. I'm pretty sure that's correct. Let me just reference that. I think I might be out by a factor of 10 there actually, but sorry, it should be 62.8 megajoules, but of course that's, I've multiplied it by 100, so therefore that takes me as gigajoules, 6.2 gigajoules, and it's not in kilograms. So 6.2 times 10 to the 9 joules minus. That's the potential energy. Right, okay, so some simple stuff first of all. However, let's make it a little bit more rigorous, mathematically rigorous. So rather than just saying this here, change in R, take out an R, etc., let's look at things more rigorously. That being, in actual fact, the change in potential with respect to the change in distance is equal to minus the, what am I talking about? Sorry, gravitational field. So what does that exactly mean? Well, let me first of all place in some radial field lines here. So this radial field, as we saw in the previous video, these field lines, remember force field, show the direction of the force on an object with mass next to this object. Okay, now, because we know that the potential is minus gm over r, if I were to take equipotential lines, like contour lines, points which join equal potentials together, you would notice that if I was jumping 100 at a time, these would start to get progressively further apart. Equipotentials. And the reason why is because if we graph the function v against r, we know that it's decreasing. It's a 1 over r relationship. So therefore this is going to spread out and continually increase. But that does mean g here is the rate of change of v over r. The rate of change of it is actually the gradient. So if I would take the gradient at a point r1, I would actually be working out g. So the gradient equals g. And we know from our previous video that g decreases as you move further away from the Earth because it's a radial field. So therefore the gradient here, very close to, would be large, because it's a large gradient, but then the further you moved away, the further the field would decrease, the gradient would decrease, the field would decrease the further out you move. Okay, so that's quite important. You might also say to yourself as well that this is another way of stating G. Another way of stating G is to say how many field lines, sorry, how many equipotentials do you cross each meter? In other words, as you move along here, the more field lines you cross in the same unit distance, the stronger G is. As you move out here, you're going to cross fewer of them in the same distance. As you move out here, even fewer of them in the same distance. So actually, it's how many you're crossing in a given distance is how strong the field is. Let me just work in, of course, therefore, how we work out the equation for potential from here to there. What happens, and it's probably a bit beyond what you need to know, but V is going to be the inverse of this. In other words, it's going to equal the integral of G minus G dr. And we're going to move that from R to 0. No, 0 to point R. 0 to point R, which in other words is the integral of minus Gm over R squared dr. And of course, when you do this integral, you increase the power and then multiply it by. And bearing in mind, G itself is negative, minus Gm over R squared, so that makes this positive. And the integral of that will merely be minus, so I bring this to minus 2 to minus 1, multiplied by Gm over R to the minus 1, between the limits of 0 and R. Good, which is the same as minus Gm over R, in effect. Good, so this is the differential form. Now this is important. That minus is also important because without that this wouldn't stay consistent. But bearing in mind the gradient of a potential distance graph, the gradient of it is G, the gravitational field, and equipotentials join up potential energies all of the same value, and they always sit at right angles to the electric field lines, gravitational field lines, sorry, getting confused. You'll do the same analogy with electric fields in a minute. So they always sit at right angles. Why do they sit at right angles? Well, if there was any force in the direction of this equipotential, then you'd be gaining energy, so it would no longer be an equipotential. So the right angle is essential. Good. Let me just show you that this does hold true for a uniform field. With a uniform field, we would have equipotentials that would be equal distance. Let's just imagine we go through 10 meters, and through the 10 meters we have changed by doing some quick maths here. 1, 2, 3. Let's put another one. 4. 1, 2, 3, 4, 5. 5 levels in 10 meters. And bearing in mind, dV by dr is minus G, we would have got, let's say, 100 joules per meter, 80 joules per meter, 60, 40, 20, 0. Nice uniform field. Equidistant because we know the potential is G delta H. It's linear, so this looks linear. My field lines do this at right angles, first of all, and showing that they're acting towards the centre of the Earth. Now, another way of writing this would be to actually take the number. So let's imagine I go through, so if that's 10 meters, each one of these is 2 meters. 2, 4, 6, 8, 10. Let's go through a change in potential of 80 joules per meter, and that has occurred in 8 meters. So what does that give us? That gives us 10 joules per meter squared, which is the same as saying 10 newtons per kilogram. In other words, it's G on Earth. If we were to move further out, and of course these would then be separating out, G would be less. If we were to move, well, let's say we go to another planet, Mars, then we might find to ourselves in 10 metres we only cross 2.5 of these. Because in 10 metres we'd only get to 50. So here, joules per metre, so therefore here what is G? G is going to be, minus there of course, it's going to be the rate of change, that's 50 over 10 metres, 50 over 10, giving us 2 newtons per kilogram. Okay, so it's linear. You might therefore ask, what's the potential with distance? You rarely have to see this, but if you know that your G is constant, that must mean your gradient is constant, so therefore it would be worth drawing something like that. But of course it would then change as it got closer to, but initially it would be very linear. And the gradient would equal 10 on Earth. Okay, so you need to feel comfortable graphing your functions as much as using equations. And perhaps it's worth me, just as an aside, okay, 2 bodies, say the Earth and the Moon, and we knew from the field lines that there's a 0 point here. So therefore, what are the field lines and equipotentials? If you can sketch the field lines and the equipotentials, then do so. Otherwise, press pause and give it a go. Otherwise, here comes the answer. Okay, so we know they're both attractive, so they're going to, and I think if you recall from the last video, they're going to do something like this. They're sort of competing against themselves, with one being more dominant than the other. They'll never cross over, they just work against one another. And if you remember, the equipotentials are always at right angles to field lines, so therefore if you follow this carefully, you can see that eventually you get to this point where there is 0 field. A point at which it cruises at constant velocity past there if it's going from one point to the other point, and also one in which the change in potential in the same given distance, there is no change in potential over the given distance. If I was to plot my potential against separation, then because they're both the same value, this goes down like that to 0. But the Moon also has a potential just like that. So the addition of the 2 would look something like that. Good, okay then. Time for one more comment on this, and that is the velocities, escape velocities. We'll often have to describe what happens as an object tries to escape to get to an infinite distance away, in which the potential, of course, is 0. So what is the kinetic energy required here if all that kinetic energy gets converted into gravitational potential energy of that value? Because remember, at the start I've got minus GPE, and I want the GPE to turn to 0. Okay, so very simply what we do is we say a half mv squared is going to equal the gravitational potential available. We get rid of those. V gives us minus gm over r, 2 over r. Square rooted. You might ask about the minus sign in there. Well, in actual fact, the way that we get rid of the minus sign is because we're going from this is actually a change in GPE, which takes us from 0 to minus GPE, that's right. So our first point is 0, because that's our finish point, and I'm looking for the difference. So I'm minusing my first point, which leaves me with a positive amount. There we go. Does that make sense? We need to be careful about those negative signs. They can really catch us out. Whether you remember to put it in the field equation here, whether you're working from the right points, from one point to another point, because the difference is the end point minus the initial point, hence the minus and the minus. Anyhow, what is it for Earth? So let's see, V, Earth, escape. That's going to be square root 2 by 6 times 10 to the 24 by 6.67 times 10 to the minus 11. Divide that by from the surface of the Earth. Gives us 11.2 times 10 to the 3 meters per second, or 11 kilometers per second. We could do the same for something like a black hole, just to make it interesting. Black hole with a mass of 10 to the 39. What's the escape velocity? Well, no, actually, should we say what's the radius of the event horizon? The event horizon is when not even light can't escape. And what's the velocity of light? 3 times 10 to the 8 meters per second. So if you think you know the answer, hit pause. Otherwise, here we go. V is root 2gm over r. This becomes c, so c squared is 2gm over r, so we get r is 2gm over c squared, 2 by 6.67, 10 to the minus 11, 10 to the 39, supermassive black hole, 3 times 10 to the 8 squared, and that gives us something in the order of 1.5 times 10 to the 12 meters. Not that large, but nonetheless, we've worked that through accurately. Okay, so just let's recap here because it gets a bit crazy. We have uniform and we have radial. We have, let's start right from scratch. The force is mg. The force for a radial field is gmm over r squared. The field G is given as linear. Field G here is gm over r squared. In other words, this is the force per unit mass. That is what G is. F over m, if you like. Okay, we move from G and we have gravitational potential energy, which is equal to mg delta h, a change in height. You can probably see now why we're talking about a change in height. And it's equal here to minus g, oh, I should have put a minus there, it's attractive force. Gm m over r. The potential, of course, G delta H, potential is Gm over r, is in actual fact the GPE per kilogram. Okay. We should also make the reference that G is minus the rate of change of potential with distance. And that will probably get us to start drawing some graphs. Let me go on this side first. The force with respect to r changes 1 over r squared, and the area here is going to be equal to force times the distance, which is the gravitational potential energy. If it were G, then the area would give us the potential. Okay, with potential and distance, which drops off as 1 over r, the gradient equals the gravitational field strength. And in drawing a uniform field, field lines sit at right angles to equipotentials, which are even for uniform, and for radial, field lines, equipotentials. Nonetheless at right angles. Good. I hope that sums it all up. Hope that makes sense.